All right, let's dive right into this explainer. Today, we're looking at a super fascinating new public research candidate from Evidence Press. It asks a highly targeted question about how machine learning systems actually shuffle their training data. When it comes to training AI, the order of the data it sees matters a whole lot. This research explores whether we can take the standard, everyday way we shuffle data and fundamentally improve it using exact mathematical certainty. So rather than trying to find the one absolute perfect, globally optimal order for data, which, spoiler alert, might be computationally impossible, this paper asks a much more practical question. Can we just make smart, mathematically certified tweaks to a standard random shuffle? Like, can we look at a random draw and only intervene when we are absolutely certain it will help? Because if we can, it could save massive amounts of time and computing power down the line. To get through this dense 55-page paper, we've broken it down into 6 quick sections: shuffling the AI deck, the certify or randomize rule, when ideal proxies fail, the impossible global order, a brutal reality check, and finally, the future of safe training. Okay, section 1, shuffling the AI deck. Before we try to optimize anything, we really need to understand the status quo, right? In machine learning, systems almost always shuffle training examples before processing them. This is known as random reshuffling, or RR for short. It's a very strong, widely studied baseline. You just choose a fresh random order, visit every example exactly once, and repeat the whole process. That is the benchmark we're trying to beat here, or at least strategically modify. To picture this, think about it like dealing a standard deck of cards to an AI model. This paper essentially asks, as those cards are dealt out in pairs, can we look at just 2 cards at a time and use math to decide which of the 2 should go first? And, more importantly, can we do this to reduce the overall error or loss of the model? Moving right along to section 2, the certify or randomize rule. Let's look at how we make those exact micro-decisions without ruining that baseline randomness. For specific, stable models, meaning the mathematical curvature or Hessian is identical across the board, the algorithm essentially treats a random shuffle like a skeleton of pairs. Think of each pair like an unflipped coin. The algorithm checks if math can definitively prove which cards should go first to lower the error. If it's mathematically certain, boom, it swaps them. If not, it just flips a fair coin. Basically, it certifies or it randomizes. Now, here is the absolute crucial point. This method comes with a built-in mathematical guarantee. It ensures that the error rate is never worse than if you just stuck with standard random reshuffling. You aren't risking a worse outcome just to try and get a better one. That safety guarantee is literally built into the original random draw itself. Which brings us to section 3, when ideal proxies fail. You might be wondering, why rely on this localized pair-by-pair coin flipping instead of designing an algorithm that looks at the whole data set and uses a simpler proxy metric to sort the whole thing at once? Well, the paper includes this fascinating proxy separation theorem. They proved that even in a tiny toy scenario with just 4 items, completely free of numerical noise because they used exact rational arithmetic, picking the quote-unquote best order based on popular idealized proxy metrics can be totally disastrous. The ratio of their final loss compared to the true optimal loss can actually grow without bound. It's wild. This whole thing brilliantly illustrates the boundaries we have to respect. We're dealing with 3 completely distinct realities here. You've got the utter failure of idealized proxies, the success of those local baseline tweaks that safely orient fair pairs, and the ultimate difficulty of global ordering. We absolutely cannot conflate them. They are 3 very distinct mathematical realities. And that leads us perfectly into section 4, the impossible global order. Speaking of global ordering, let's explore why arranging the perfect deck from scratch is actually a computational nightmare. There's actually zero contradiction between making these safe local moves and the sheer impossibility of global ordering. Resolving a fair binary choice locally, just flipping those pairs inside the random skeleton, is totally safe and verifiable. But the global problem, sorting every single piece of data from scratch, that exposes the full combinatorial burden. It is totally intractable. To get specific, the paper proves that global ordering is mathematically NP-complete, basically a worst-case computational nightmare, when a metric called the stable step size hits 2. But there is a catch here. If you keep a safe distance from that edge, you can actually approximate it. So there is this really sharply bounded cliff between what's possible and what's completely impossible. All right, section 5, a brutal reality check. Okay, let's dive into, honestly, the most refreshing and kind of unusual part of this entire paper, the radical transparency. In an AI industry that is frankly obsessed with hype and constantly claiming the next big speed up, this research paper explicitly states that their registered 32 instance Matrix 3 pilot established absolutely zero practical neural network speed up. It completely failed its own practical feasibility gate. Let's break down why that happened. Basically, calculating the exact conditional value was just way too computationally expensive. They used strict error controls, and hey, the good news is the safety logic worked perfectly. There were zero false certified signs on the grid. But the bad news? The lower degree approximations certified nothing at all, and the higher degree approximations failed to provide enough coverage as the problem size grew. So the method rarely certified a decision, defaulting back to random reshuffling almost every single time. This perfectly illustrates why this kind of transparency is a real game changer. As the authors themselves put it, a method that rarely certifies a decision simply falls back to RR and cannot justify its extra cost. If you're spending immense computing power just to check if an order is better, but you end up falling back to random anyway, you haven't optimized anything in the real world, you've just burned time and money. So, where does this leave us? Section 6, the future of safe training. Is this just a dead end? Actually, far from it. The true value of this candidate isn't about getting immediate wall clock speed today. Rather, it introduces a powerful new research design principle, creating an interface that acts when it is absolutely mathematically certain and safely falls back to randomness when it is not. It's essentially a fail-safe right at the decision level. To actually make this practical in the future, the authors lay out a very strict sequence of next projects. First up, researchers need to establish validity margins for more complex, heterogeneous data. Then, they need to develop coverage-first compression techniques so the system can certify decisions way more often. They also plan to formalize more of the analytic proofs using Lean, which is a proof assistant, and finally, push for independent specialists to reconstruct the proofs without using the original production verifiers. While this specific pilot definitely failed to beat the clock today, it successfully mapped the exact boundary between what is mathematically possible and what is practically feasible right now. And it leaves us with a massive, lingering question. If we can eventually engineer these certificates to be computationally cheap, what happens to the limits of machine learning when AI can finally train with exact, certified certainty?